5, 4, 3, 2, 1.
Hey, it's me, Destin. Welcome back to Smarter Every Day. I love rockets. If you've been around this channel, you know that about me. And today is like the best day ever because we're gonna learn how to build rockets. Just down the road from Huntsville, Alabama, there's a city named Decatur. And in that city, there is a rocket factory owned by a company called United Launch Alliance. And that factory has been cranking out incredibly reliable rockets for years. Because these orbital rockets have some of the same technologies in them as ballistic missiles, the knowledge about how to build them is protected. In the United States, we have a set of regulations called ITAR, International Traffic in Arms Regulations. Because of ITAR, nobody's going to let you walk into a rocket plant with a camera and film things. They can't risk that stuff getting out and breaking the law. So there has to be an incredible amount of trust between the parties that want to film things and the people that own the plant. Thankfully, I was given the opportunity to build that trust with ULA when I went and watched the launch of the Parker Solar Probe and I met the CEO of ULA on the launch pad. If you haven't heard of this guy, Tory Bruno, then you're in for a treat. He's a legitimate rocket scientist who knows his stuff inside and out. It was at this launch that Tory and I built trust with each other. Like, this guy is the real deal. The tour we're about to go on has never been done on the internet. Tory literally takes us right up to the line of what he can show us, and all along the way he's answering my technical questions and he's letting me explore the factory. So here we go. Let's take the first ever online tour of the United Launch Alliance rocket factory in Decatur, Alabama with the CEO of ULA, Tory Bruno. Okay, we've got Tory mic'd up now, and you're gonna show me the rockets that are fabricated at this facility? Yeah. What do we have here?
Okay, so we've got an Atlas V on the side. This is kind of our workhorse, and it's in the 5-meter payload fairing configuration. So that's what we're talking about here. It also has its SRBs on the side, which is sort of its maximum lift version. When it's got all 5 of those, we call it the Beast.
And this is the Delta IV Heavy, and this is what you thank you again for letting me participate, or at least see the Parker Solar Probe launch.
That was fun, huh?
And that's fabricated here in Decatur.
Yes, yeah. So 3-core rocket, literally 3 rockets kind of bolted together. And it is our largest rocket. It's physically the largest rocket in the world right now, and it is what we used for Parker Solar Probe.
And this is what I want to talk about.
Yeah.
This is Vulcan, and this rocket has never flown.
Never flown, not yet. And you're going to see the first flight vehicle hardware in the factory being fabricated when we go in there today.
Today?
Yeah.
Okay.
So this is our brand new rocket. You can think of it as kind of a derivative of those two in a way. So it'll be large, 5.4 meter diameter, so a little bit bigger than Delta. It can take 6 SRBs. It's a huge cavernous payload volume for the spacecraft. And this rocket has 30% more lift capability than this big 3-core monster.
So when you say 6 SRBs,
be 6 of them,
and that's just to get out of the Earth's gravity well.
Yes, right, exactly.
Can we go see the stuff?
Yeah, let's go see it.
Okay, we're at a rocket factory. Let's do it.
We're gonna peel off to the right here.
Okay. Okay, I'm seeing the grid here.
Yeah, so this is a barrel section from the booster over your head, actually from an Atlas. And I'm going to walk you down to the end of the factory where this first gets made. It's the first thing we do. Kind of raw stock comes in the back door, gets machined, puts this curve in it, and then we'll walk you all the way through to a completed version.
That's awesome. Okay, so there's something unique about the North Alabama area here. Correct me if I'm wrong, but there's a little triangle. There's a nuclear power station. There's a steel mill.
Yes.
And there's also a rocket factory, like in a triangle.
That's true.
And then you got a river running between them.
Yep.
And so you can bring in steel, you can make a rocket using the power from the nuclear plant.
Yes.
Is that why you're here?
That's part of why we're here, but it's also because of the talent that we have here with the University of Alabama and the other Alabama universities and the technician programs they have here. You just get an awesome workforce. And with the river, which is only a mile from here down Red Hat Road, we have the dock for our rocket ship so that we can transport our rockets out to the launch pad.
This is the rocket ship Tori's talking about. You see? It says so right on the side, rocket ship. Rocket ship navigates its way through several rivers up to the Mississippi River, down to the Gulf of Mexico, and then it heads to whatever pad the rockets will launch from.
In fact, you should come back sometime and do the ship.
Yeah, I should ride on the ship.
Yeah.
Is that a thing? Can you do that?
Yes, that is a thing.
Okay, we're getting on a golf cart and we have to cut cameras because we're gonna pass, not secret stuff, but things we can't film, right?
Right.
Okay, cutting the camera off. Okay, we're on the golf cart and I've obtained permission to film straight up so you can't see that, which is pretty neat. Okay, so I can't talk about that right now, can I?
No, we can't show it to you, but I can tell you what it is. That's a Delta payload fairing. So one of the smaller versions of the Delta's payload fairing, and then you're passing by a heat shield here that would protect the RS-68 engine from its own plume during flight.
Okay, this is almost emotional. I mean, you know what it's like to sit in class and study this stuff.
Sure.
And then, because you went to Cal Poly, right?
Right.
Yeah, so this is me looking at all the stuff I've learned about and finally getting to see it. It's one thing to see it on the pad, but it's almost like a holy experience.
Yeah, well, you're inside where it's actually happening, all getting put together.
Okay, it's starting to get the smell of the machine shop, the manufacturing, the cooling oil smell.
You got it.
It's my understanding you're about to show me how to build a rocket from scratch.
Yes, I am.
Okay, excellent. So we're going to the door, right?
Yes, we are.
Okay, this is what I wanted to see here at ULA. This is the door. I can't even get, it's a wide angle lens. So that's the door where the material comes in, right?
Right, that's where the raw aluminum plate and other materials come in. And then this is the receiving area. And as they move that way, they turn into a rocket.
So we're about to build a rocket by going that way in the plant.
Exactly.
Okay, I'm game, let's do this.
All right, let's do it.
Yeah. And this is an active manufacturing facility, so you're just gonna have to deal with the audio. There's a lot of tools going on out here.
Yeah, sorry about that. But you know, building rockets.
That's good. Oh wow, that is really, can I go touch that?
Yeah, absolutely.
This is a very, very expensive piece. Is that aluminum or stainless?
That's aluminum.
Aluminum.
Yeah.
And is that fabricated here locally? That's imported.
No, so we buy that from a supplier.
Okay.
And then it's shipped here, comes in through the big door, if you will, and then we machine it down. We're going to remove more than 2/3 of the material while retaining about 90% of the strength.
In certain dimensions, right?
And I will show you that, yeah.
Okay, got it. So this is our raw material, and we're gonna go make a rocket. Okay. Rocket.
All right.
And so all this is aluminum.
All this is aluminum.
That's a unique dimension. You normally don't see plates of aluminum that wide and that long.
No, so this is actually made especially for us in these dimensions so that we can turn them into the barrel, the propellant tanks of the rocket itself.
Okay, so you're tooling up an entire foundry of some type, or a mill, a rolling mill.
A rolling mill.
Okay, gotcha.
So I'm going to show you a couple of different things before we get to the machine. So starting here with the raw stock of 7000 series aluminum, it'll eventually become a round rocket barrel. This is just after machining, and I wanted to point this out to you because this is our old style of grid that we machine in, called an iso grid, and you're familiar with what an iso grid is,
yes.
right? So we have isentropic properties when we do the stress analysis, and you can see the triangular patterns in there. That's not actually the ideal pattern for a rocket barrel, but it is what the analytical tools, the finite element analysis tools available to us when we designed Atlas and Delta in the 90s were available to us, and that's why we have that pattern. Vulcan will be better because the tools are better, and you'll see the difference when we walk down the line.
I have never thought about that. So literally, because in the 90s, the FEA analysis could solve a triangle easily.
Yes.
That's why the iso grid is a triangle. I would have never thought that. So so basically, if I understand correctly, can I touch this?
Yeah.
I'm going to ask you that every time.
Yeah,
so basically,
right.
Because you can compute the force coming in one member to a node and the forces coming out the other member, that's how you get arrived at iso grid.
Exactly.
Okay, fantastic.
Yeah, it's sort of an interesting thing in the real world, how the engineering tools that are available dictate the kind of designs that we use.
Got it. What's your safety factor on flying here?
Oh, so it depends on what part of the rocket we're talking about. Anything that would be pressurized when people are around it has a higher safety factor than what is not. But the basic factors we work with in flight are anywhere from 1.1 to never really higher than 1.25.
Got it. Yes. I mean, it's very different than like designing a railroad car where your factor of safety might be 7 or 8.
Oh no, yeah.
And a factor of safety is if you can compute the stress that the thing will break at, you design it to 1.1 times that.
Right, 10% more load carrying capability, and really a factor of safety is really a factor of ignorance. You have a factor of safety because you're not truly sure what might happen to it in the field, so you give yourself just a little bit more. And you talked about rail. Big tractors are another one where you have big factors of safety, like 7 times, 12 times. When we do rockets, we like to keep it closer to like just 10%, maybe 20%, because we can't afford the weight.
Got it, because every extra thousandth of an inch that you put in this webbing here over the course of a huge part like this, you're talking tons on the whole rocket.
Yes.
Okay.
Exactly, and this is a booster plate, and so every 7 pounds of that costs me a pound of spacecraft.
So how long does it take to machine that? You have the tools here to machine this isogrid.
Yeah, this is about a 2-day operation altogether.
Is this curled like a potato chip in this direction or in this direction?
In the long direction.
In the long direction.
And you're going to see that operation as we walk to the other end.
Okay, perfect.
That's what the 25-ton brake presses are for.
Yeah, because if you're curling along the long direction, you require a tremendous amount of force, and you have to have alignment to keep it straight during the bend.
Exactly.
Okay. Is that a pressure vessel? I mean, would that hold pressure, or would there be a liner on the inside?
It is a pressure vessel, but actually on the booster, because it's liquid propellant, most of the pressure is at the bottom just coming from hydraulic head. We only have a few psi of gas on top to keep the propellant down against the outlet, feeding it into the engine.
Got it. This is not something I expected to see. These guys they appear to be are they washing? What are they doing?
They are. So the first thing that happens to those big plates is we plane them. We make them flat. And so these guys are going over an operation that's just been done. They're cleaning it up. They're looking for any imperfections. And what you're going to see in the factory that I think is really cool, we're building rockets, sort of the pinnacle of technology, and you're going to see high-tech robotic operations, but mixed in, you're going to also see craftsmanship with people who are very skilled and have great attention to detail, like these guys. They're going to go over every inch of that thing and make sure that the automated machine that planed it didn't leave any features we don't want.
So if like a piece of the tool broke or something like
exactly. that. Exactly, chatter, whatever.
Yeah, so are these your fly cutters here?
Yeah, basically end mills. Some of them are side mills, but yes.
Gotcha. Am I allowed to look at this fly cutter?
Yeah, go ahead. Sure.
Wow.
Isn't that cool?
I love machining. It's a secret passion of mine.
Yeah, me too.
Yeah.
So you went to Alabama, right?
I did.
So do you guys do a lot of sort of machine shop time in your engineering degree?
Not a whole lot, but we do take a class or two. For my undergrad, I did that.
Yeah.
But my dad had an old lathe and mill in the garage when I was growing up.
Cool.
Yeah, that's cool stuff.
The other thing I'll share with you, you can see all that flow down there. We actually recover all of these chips. So even though we're going to take the majority of the material away by machining it off, subtractive manufacturing, we capture all of it, we send it right back to the supplier, and it comes back to us in a plate, a month later.
That's awesome. Is that coolant?
That's coolant, but it's mostly water. Mostly water. So it's capturing the chips.
That's a tremendous amount of water flow.
Yeah, well, chips are heavy.
Hard to get a scale for that. It's hard to get a scale for that, but that is a lot of fluid. Oh, there's a whole river of coolant there.
Oh yeah. Yeah, you can see it.
And are you looking for places where the tooling broke?
No, we're looking for chips or debris that may be on it. We only have plus or minus 5 thousandths on the thickness.
Right.
So a small chip would be outside of the tolerance zone.
Right. Thank you very much. My name's Destin.
Jeff.
Nice to meet you, Jeff. Nice to meet you. That's cool. The human story is what's really cool to me. That's amazing.
Me too. Here's one that I think this guy's actually running. So you can see way down there where the cutting head is. These are actually the plates for Vulcan Flight 2.
Really?
The second Vulcan that'll go. So you know what we ought to do is we ought to like steal you a chip down there, so you'll have a chip from the Vulcan rocket when it goes to space.
Can I stick one in my pocket?
Yeah.
Okay.
They're a little sharp. Be careful.
I will be careful. I'll take a little one.
Nothing to see here.
There you go. Chip for Vulcan. There's your chip. Guard it with your life. All right.
We're in trouble, but don't tell anybody.
We're in trouble. Don't tell anybody. Tori Bruno said it was okay if I stuck a chip in my pocket. So these machines are CNC, correct?
Yes.
Okay, and are these specially made machine, or are these, because usually you don't plane a surface that wide?
No, generally when you're in this kind of factory, you're going to see tooling that comes from big tooling manufacturers, but it has been designed especially for this application. So all of this is custom stuff.
Really? So, for example, the head here is probably normal, but the waves on the machine, this is incredibly long for a mill.
Yes, exactly. Very, very long and very large.
Gotcha.
Very, big width. That lets us do more than one plate at a time.
So if one of these machines go down, what does that do to you?
That would be a big impact, but fortunately we have more than one, so we would always still have the other machines running. And so what would happen is we'd get it fixed and then we would catch up on an off shift.
Because I've kept up with your launch record and you always meet schedule. Is it because you have redundancy built into this part of the process?
That is part of it. So yes, this factory was actually built with the idea in mind of building as many as 40 rockets a year. And so we have so much capacity, it's easy for us to kind of make up for little challenges like that along the way. Because nowadays you fly maybe 12 or 15 times a year tops.
Right. Okay, so you're not at capacity.
No, not even close.
But you want to be. This is a commercial
for that.
Yes,
we do. Yeah, we do.
Okay, so that moment right there where Tori Bruno is joking about the capacity of his rocket plant, it reminds me of a very specific moment in an audiobook I love called 7 Eves. Now, the beautiful thing about Smarter Every Day being sponsored by Audible is I can use moments like that to go to Nashville and introduce you to someone I've been wanting to meet for a really long time. Okay, so we're gonna drive a couple hours away and we're gonna meet a lady named Mary Robinette Kowal. She was the narrator for 7 Eves by Neil Stephenson, and she did an amazing job. Listen to the first line of the book.
The moon blew up without warning and for no apparent reason.
Let's go talk to Mary Robinette about this book. What a cool place to meet someone for the first time. I'm Destin. You doing all right?
Yeah, I'm doing great. Nice to meet you.
Good to meet you. You doing okay? Okay, this is Mary Robinette Kowal, who is an amazing narrator of audiobooks.
Thanks.
You are. I've spent like well over 12 hours with you, mostly in a tractor, but that's another story. But the book that I want to tell people about is called 7 Eves by Neil Stephenson. And this looks like it was a challenging book to narrate.
It was more than a little bit challenging. It's technically completely accurate. It's got this huge international cast. So basically something hits the moon, they never figure out what it is, shatters it, and that causes them to have to get off the planet real darn fast because the pieces of the moon are going to start raining down and causing destruction for 5,000 years.
Mass destruction. This is why I wanted to do it on this video, because Tori Bruno is talking about building more rockets, but you've also written a book yourself. You've written many books, but there's one in particular that's similar to 7 Eves.
The Calculating Stars. Yeah, I slam an asteroid into Washington, D.C. in 1952, which kicks off the space program fast.
Also building a lot of rockets.
A lot of rockets.
There you go. So go get one of these two books. She's kind of downplaying that a little bit. You've won the Hugo Award, the Locust Award, and the Nebula.
That is correct.
For that book. That's a big deal to win all three. Go get her books. Audible.com/smarter, or text the word smarter to 500-500. Which one would you recommend?
7 Eves.
7 Eves? I'm going to recommend your book, even though I haven't read it. I'm guessing it's going to be amazing. It's called?
The Calculating Stars.
The Calculating Stars. Okay, that's it. Let's go back and build more rockets with Tori Bruno. Here we go. Yeah, so if anybody needs their own personal rocket, Tori's your guy.
Oh yeah, just let me know. So you remember we were looking at ISO grids down there when we were looking at those delta panels. So if you look at this panel that's being machined, you can see that they're rectangles. So this is an ortho grid, which is not symmetric, but we're able to do that now because the engineering analysis tools are better. And so Vulcan switches to OrthoGrid, takes about half the amount of time to manufacture, and these panels will actually be stronger.
So as I look along the OrthoGrid here, so you're going to break it along the long side. So this is going to be a really long, skinny potato chip looking thing.
Exactly.
So what happens when you're breaking along that line? Because you have a section in the middle of the webbing that's going to have the most stress.
Yes.
But along the longitudinal webbing, you're going to have, it's going to be difficult there.
So actually the way the break process works is we'll bring it in flat, and as we break it, we're moving just a small amount of material each time, and we roll the part in and out. So the amount of strain and work hardening that we get is actually very uniform across that width.
Okay, got it.
But the issue that you brought up is one of the reasons why that's done by people. It's a hand operation. So there's no CNC on the curving or the brake press. It's all craftsmanship.
Really? That's amazing. So these are Vulcan?
Yes, these are Vulcan panels. These panels are going to space.
Wow, it's got a lubricant on it, it feels like.
From the machining.
Got it.
From the machining
Got
process.
it. And so the OrthoGrid, just looking at it, the webbing looks thinner, so it looks like it's much more lightweight.
It is, yes.
Are you allowed to tell me a percentage?
I can't give you the number yet.
Okay.
Ask me next year.
Okay, I'll do that.
But it is absolutely lighter weight and stronger than the old IsoGrid design. And it takes half as long to make.
Why does it take less time to make?
You can see how much simpler that pattern is. So the CNC machine has more straight runs and a simpler pattern, and it's that much faster to machine.
So those are fancy space sawhorses.
Yes, they are. Yeah. So these are the panels that have been machined. They've been cleaned up a little bit, and they're getting ready to go into these 25-ton brake presses, bump presses, in order to potato chip them up into a curve.
Okay. Those presses right there.
Those presses right there.
Okay. So I'm noticing that there's no hydraulic pressure in the center of the press. There's just a really, it's a strong back.
It's a strong back.
What is the technical term for it?
Strong back.
Is it really?
Yeah.
Okay, awesome. So can I look at this and then look at that?
Absolutely.
Okay, am I allowed to walk over there?
Yeah. So you can see that these guys actually have a little bit of curvature along their length. We're going to actually take that out. That helps us form the curvature along this axis more evenly. So it's sort of an intermediate manufacturing step, if you will.
Is it done on purpose, or is it a function of stress relief?
It is done on purpose.
Oh, okay.
Yeah.
Gotcha.
And of course, this is, again, IsoGrid.
IsoGrid. Got it. So this is Atlas 5.
Right.
Okay. So at some point you have internal stresses in the material.
Yes.
How do you have an oven here to anneal?
No, we let them what's called artificial aging of aluminum. So 7000 series will do that. So we're going to put a certain amount of work hardening in here, and we like that. We actually like the properties that gives us. And then what the sort of room temperature artificial aging does is even that out for us.
So we're entering the space of, I notice you're saying hello to everyone. People know you, don't they?
Yeah. Oh yeah.
Yeah, it's cool. So we're entering the area where we've got this tooling here that's holding this stuff. And these are the guys. Oh, they're actually doing something now.
Yeah. So that's that's a skirt, and they have just manufactured it. Just put the curve into it. We can walk over there. We'll let them finish what they're doing. We can talk to them if you like.
Okay. Yeah, that'd be great. This is a finished part here.
Yes.
That's Vulcan.
Vulcan flight hardware right here. It takes 5 of these to make a complete barrel for a methane tank, and then another 5 on top of that will be the liquid oxygen tank. And we're going to show you friction stir welding, which is how these are joined.
Gotcha.
All right, so here is our 2 25-ton bump presses. So this big beam in the center is very, very stiff. That's why it's so tall, because the hydraulics are on the edges. And what the technicians are going to do, our craftsmen are going to take one of these big flat panels on these roller carts, and they literally have patterns that are pre-formed that we've made, and they're going to roll them in and out and have that knife edge come down and hit it and slowly potato chip it up while they're matching it to the physical pattern until they have it just right. And so we saw all this high-tech computer-controlled machining down there. Now this is pure craftsmanship where they're going to do it by eye and by pattern and achieve very tight tolerances in doing so.
Do you have any plans to computer control this in the future?
No, this is a process that you will always get better results doing it by hand.
That's amazing. So, I didn't even think about having to hold the material as it comes out.
Exactly, yeah. Let's walk down and you'll see one, they're working on that one right there.
Okay.
That's a skirt, which is why it's short. Hey guys.
So one question I have, Tori, is as they lift the part, obviously it's being supported by the top, it's going to deflect.
Yes.
So how do they know if they, it's pressing now.
Yeah, so you can watch and you'll see. They're lifting it a little bit. He's bumping it again. So now they're making another adjustment and they're going to bump it again. This is all done by eye and by hand. You could do this with a sort of a remote controlled operation, but you could not get the same lightweight tanks out of that. You'd have to work with much thicker pieces of metal and you wouldn't have as high a performing rocket.
So I notice she's looking with her eyes. She's operating, is she operating the press with her foot?
Yes.
She's operating the overhead crane.
Yes.
And also that...
And she has what's called a walk-along or a creeper, just like you would have, say, on your truck to tighten a fence or to get yourself out of a ditch. She's doing all three things at once while watching the curvature she's creating in this part.
She is fully engaged.
Oh, yes.
That's amazing. Don't look at us. Don't let us distract you. Should we go away? We're distracting them.
Yes, yeah.
Let's go.
Yeah, we don't want to have the destinatory discrepancy report on that. All right, and here is finished product. And this is all for Atlas, as you can tell by seeing the ISO grid. And then we're going to walk down the aisle and we're going to show you how these get joined together into a tube. Welding. Oh, I almost forgot. We got to go. Yeah, we want to go to chem processing, right?
Oh yeah, see stuff anodized?
Yeah,
Let's do it. Yeah.
Okay, so now we're in one of the world's largest plating facilities or chemical processing facilities where we're going to etch the panels down so that we have a very consistent, high quality known surface. And then we'll anodize them, which is plating to create a very thick oxide layer to give the aluminum corrosion resistance and a little bit of hardness.
Oh, that is a very specific tool there.
Yes, it is.
To hold that part.
Yep. You know all this, Destin, but this is sort of classic bare aluminum. It automatically forms its own oxide layer right away, which is why it's sort of white in color. But we don't get very good corrosion resistance naturally, especially from a 7000 series aluminum, because it's not very thick and it tends to be porous. And so that's why we anodize it.
That's bad for fatigue, right?
Yes.
Okay.
Yes, very bad. So we can get a phenomenon called stress corrosion cracking, for example, if we allow corrosion to be present in these kinds of materials.
So is this the chemical milling process before you anodize?
No, that'll all happen inside the booths we're going to take you to. This is really for cleaning, because we're going to, there's a lot of machining activity, there's a lot of chemicals that are going to be involved, and so we like to have a known condition when it goes in and out of the tanks. And this particular dome is in here to be inspected.
Look at that.
Yeah.
So what am I looking at?
So you're looking at us rinsing and washing a ring before it comes further down into this booth, which is actually an inspection booth.
Gotcha. So this is pre-anodization.
Yes.
So just to connect the parts, we made the part down there, pulled it up on this crane,
right,
pulled it over here,
brought it over there and inspected it one more time. We're going to take it down there and clean it. We're going to inspect it, And then we're going to go around where you can't see right now and anodize it.
And we're gonna drop it off the other side?
And then when it's all done, it'll come down the other side.
Gotcha. So this is like the rainbow arc of anodization.
Yes,
if
it
you will.
is.
Okay,
Yeah.
cool. So Shannon, what's your role here?
So I work on the commercial crew hardware.
Okay.
I'm the production and engineering group, so I work with the design team and the technicians to interpret the drawings and make sure they're building it correctly and give them all of the procedures and processes that they need.
What kind of engineer are you?
So I'm in the production engineering group, so like manufacturing engineering.
Wow.
How's it going? That's the thing about working at ULA. You never know when the CEO is going to walk in on you cleaning the floor. So you said sulfuric acid to do the etching?
Yes, and that's part of the plating. So anodization always uses typically one of three acids. Use sulfuric, use chromic acid, or other organic acid. So that's part of it, because that releases the oxygen in the bath. That ends, some of it bubbles off, but the rest of it ends up attaching to the material, creating that corrosion resistant layer.
So this is a vat that you would dip the part into?
Yes, in fact, here we are. Here's our sulfuric acid anodization. So there's a part in there right now. It's going to sit there for a prescribed amount of time. It's heated, and then we're passing current through it, because ultimately this is actually a plating process. See, here's our DI tap water rinse we were talking about. Yeah.
So you literally put the part in there and you give it a shower?
Give it a shower.
That's awesome. Holy cow, that's intimidating.
Yeah.
That's intimidating.
Yeah, keep your hands out of there. Yeah. We'll plate, we'll rinse, we'll plate again, we'll clean, then it goes out where you were before for inspection. Here's what they look like when they come out. So you can see that sort of characteristic green bronze color of an anodized aluminum surface. And as they naturally age, it'll become more and more bronze. So when you see an Atlas rocket on the pad and you look at the booster, it has that very distinctive bronze color. This is why, because of what we just looked at here. Maybe we'll just let you peek over the edge. Would you like to?
Yeah, that'd be great.
So at this point, we finished plating, cleaning, and inspecting, and here are the panels lowered down from where we took that last shot.
And now what?
Now they're going to get friction stir welded together into barrels, forming the body of the rocket and the propellant tanks.
So one question I have about this next step is, when you weld something, usually you tack it together all around the perimeter before you do the final welding, because the heat will draw it up.
Right.
So how do you account for that here?
So we fixture it, we hold it in place mechanically, because the interesting thing and the reason you want to do a friction stir welding is because you don't melt any material. Conventional welding, you bring the parts together, and then as you say, you tack them to hold them, and then you fill in that gap with filler material that you've melted that fuses to the parent material, melting it a little bit too, and then you get a heat affected zone, and that entire weld joint has different mechanical properties than the original material. But when you friction stir weld, you never melt anything. You bring the parts tightly together, and you bring a head that spins and literally stirs the material together as it moves. That gives you a stronger joint, which means you can thin down the entire part and get a much lighter weight, higher performance structure.
So what is the head made out of that can withstand the temperatures?
So the heads are always made out of tool steel, high strength materials that can stand that over and over and over. We're welding aluminum, so we just need that difference.
So the melting point of aluminum is so much lower than the head of the tool part, or
it
whatever you call it.
never quite melts. It gets warm, it gets a little soft because of the heat generated through the friction, but we never actually erase all of its mechanical properties like you do with a classic conventional fusion welding. You literally melt the material.
And I'm not allowed to film this, and I'm not allowed to film that.
Nope.
What if I peek over there? Can I peek?
You can peek.
Peek over there, but it was blocked out, so people couldn't see that.
So now those big plates that you saw machined and you saw bent and you saw anodized have to get friction stir welded together into a barrel to form an Atlas booster, or in the case of what you see over there right now is the Vulcan first flight liquid oxygen tank.
That's it. Okay, so that is the first vertical assembly of Vulcan.
Right. And so that tank will go to space and it will lift the Astrobotic Peregrine lander back to the moon, which is our first mission on Vulcan.
Really?
Yeah.
I didn't know you had a lunar mission.
Yeah, that's our first mission.
That's awesome.
Yeah, it's super
Okay.
cool. We're really excited about that.
Yeah.
So what you're seeing here is 5, these are actually Atlas, but for the version that's Vulcan, 5 of those big panels that start out flat and thick, machined down, they're fixtured up in there, and if you look right there, you can see that sort of bright aluminum stripe that runs up it. That is a completed friction stir weld.
And you have a rotary stage at the bottom that's turning it, and so you have the weld on one
Because we're going
side.
to do 1, 2, 3, it takes 5 of those panels to make a Vulcan, so we got to do 5, we got to do all of those welds. So
Wow.
it'll rotate it, and we'll do another one, rotate it, do another one. And over there is a finished Atlas barrel, if you'd like to kind of see what it looks like.
Yeah. These are friction stir welds?
Yeah. So this is an Atlas tank, and by the way, you can, maybe it's a little hard to see from down the ground, but this is a lot smaller than that big beast over there.
Right.
And so here's our classic isogrid pattern.
What's our diameter on Atlas?
So Atlas is a little bit closer to like 3.8 meters, and this is a 5.4 meter diameter rocket on Vulcan.
Got it.
So even just a little bit bigger than Delta.
That's a lot more volume payload.
Oh yeah, yeah. So R squared, you know the math.
Yeah, so like it's better to order 1 large pizza than 2 medium pizzas.
That's right.
And so when you have a large rocket, you get more than just 2 small rockets.
You got it.
That's the easiest way to say that. Okay. So this is a friction stir
So
weld.
here's a friction stir weld, so you can feel that.
Yeah, you can feel where it heated up and grew a little bit.
Yeah. We just bring these parts tightly together. We bring a head down that spins very, very fast. It heats it, softens it, stirs it together without ever melting it, and we just run all the way down the length of the barrel. And that's how we join them together, and we get a stronger part and a lighter rocket.
But do you do that on both sides? I guess my question is, do you have a tool on the outside
Yes,
and the inside?
yeah, you have to react against something. So there is such a thing as a self-reaction friction stir weld, and I'll show you that too.
Okay.
But for these parts, yeah, you have to react it against, so you don't just push the material through.
Gotcha.
So now we're going to look at a different friction stir welding process called circumferential, because we're going to attach a dome or a barrel. Self-reacting friction stir welding, where we don't have to have something holding the part up from behind.
It seems like that would be difficult though, because like when you have a hammer and you're hitting something on an anvil, you know, it squishes and molds the metal together against
Yes.
the anvil.
Right.
But if you're just pushing, how does it not just push out the other side?
Well, it has to do with how we fixture it and some very clever things in the friction stir weld head, which is why I'm not going to let you film it.
I can't film it?
No.
Okay.
You cannot look at that part at the end of this big assembly up there.
Which
That's
part
the
can I
weld
not look
head.
at?
Yeah, this guy right up here. So
That
at the
part
end of
I
that-
can't look at.
Don't look at that.
Okay, got it.
This is
little video
why
magic.
we're taking your card.
This is why you're taking my card, because of ITAR. It seems like you would be more prone to fracture on the back side.
You are. There is some tricks and techniques to making this work well, especially a self-reacting process like this one, where you don't have any support to protect that joint.
And what's the advantage of doing that? You can seal a tank. It's like when you sew a pillow together, that last stitch is important, but you have to do it from outside the pillow.
One of the things that we have to deal with is when you come around, because of the way that head works, you actually leave a terminal hole. So where you terminate, there's a hole that penetrates the tank that we then later have to seal up as well. But it's worth doing that because this process is so fast.
This tooling here
So a
holds
big
everything.
tank like the tube we just filmed would come all the way down here, where we would either have a dome or a ring that would then get the friction stir weld to put it all together
on the circumference.
on the circumference.
Got it. So there's 2 different operations. There's a longitudinal friction stir weld, and there's a circumferential
Exactly.
friction stir weld.
In fact, you can see a dome over there that's being set up for its attachment.
So that's a smaller tank. So would that be oxygen?
Yeah, that's Atlas. That's just the dome. That's just the dome attached to its ring. It'll get attached to a big long barrel.
Gotcha. Sounds good.
Okay. All right. And there's an X-ray booth to X-ray joints, and then there's also a pressure booth where small bottles get pressurized, and then outside this building there's a booth where we put pressure and fluid in the big tanks to make sure everything seals, just like any normal kind of pressure vessel process.
So this is humans know how to make pressure vessels. So you build it, you weld it, you seal it, and then you take it up to a certain pressure above what you think it's going to see, and that tests it, and then you come back down and then you fly it.
You got it.
After the booster is assembled, the plumbing is installed, the insulation is applied as necessary, and the rocket engines are mounted. We weren't able to film details about the engines themselves, but they're made off-site by a variety of different sources. It's really interesting being able to peek inside and see the ISO grid and understand where we started with the plate.
Yeah.
That's pretty fascinating.
All right, so we built the booster. Now we're going to talk about the second stage of that rocket,
Okay.
the part that goes to space. So the technology we had before that we walked through was aluminum, rigid structures, very high performance. But on a booster, you know, you could afford 7 kilograms of inert mass before it costs you a kilogram of spacecraft. On the upper stage, it's literally 1-to-1. So we switched to an even higher performance technology. So now we're going to walk the Centaur line, our very high performance upper stage. We use stainless steel.
Well, to be clear, the Centaur is like, it's like the tractor. It's the heartbeat of American space, kind of, right?
Yeah. So it is in fact the highest performance upper stage ever flown. It is the last stage of the rocket that takes the spacecraft all the way into space and to its destination orbit.
Gotcha. Okay.
All right, so this is a Gore, and these are kind of fun. These are going to be resistance welded. You can't friction stir weld them because the material is too thin, and shaped into a dome. And you can touch this if you want, Destin. That's it.
Oh my goodness. And that's a pressure vessel?
That's a pressure vessel, and it's going to be huge.
Okay, I had no idea.
It'll be over 3 meters in diameter, 40 feet long.
So I can just tell you this, like I've done the math to say if I have a certain thickness pressure vessel, it'll be this much weight, but it's a totally different thing to actually feel it.
Oh yeah.
It's like, it's just nothing. It's nothing.
Nothing there, nothing there.
That's amazing. Okay, I can
Half
understand.
the thickness of a dime.
Wow, okay.
Yeah.
That's incredible. And so you put these together in a sphere?
We'll put those together in a dome, and then there'll be a cylindrical section that's almost 40 feet long, and then another dome on the bottom. So this stuff comes in big coil rolls, almost like you would buy sheet steel, you know, at Home Depot or something. And then we stretch it, and we cut it into those shapes. And even as thin as that is, we'll actually machine it still, kind of honing it to get even just a little bit thinner than we can buy it. So these are sharp edges, so be careful. But it came off a big roll, and we've laid it out, we've cut it.
It is all stainless steel. So these are they called mandrels? Or no, not mandrels. What are these called? These are dies.
So these are dies, and they're going to be used to stretch it and cut it for those Gore shapes that you saw for a dome.
Okay. That really gives you a sense of how little material and the margins you're playing with here.
Yeah, and then we didn't talk about it, but the 5-meter composite payload fairing for Atlas used to be made in Switzerland by a company called Ruag. They're going to make the Vulcan 5-meter payload fairing, and so I asked them, this is another one of those strategic business partnerships, to take their factory out of Switzerland, and it's actually on the other side of that wall.
Really? So you brought the factory to America?
Brought the factory to America.
And there was enough volume there that they were totally on board?
Yeah. One of the strategies for having a very successful first flight on Vulcan is to fly it before you fly it.
With parts from Atlas.
You got it. So lots of the technologies on Vulcan could be flown on Atlas. And so we'll slowly start bringing them into Atlas over the next year. We'll fly Vulcan payload fairings on Atlas. We'll fly a lot of the same technology you just saw. Pretty much everything but the BE-4 engine will have flown on Atlas at least once before we try it out on Vulcan.
Gotcha. I noticed you have pictures of the commercial crew all over the walls here.
Yes. Yeah, so we're flying people. That's a whole nother game. You know, 135 in a row is we're very proud of that. But when it's a person up there, when you can shake hands with the payload talk to them and meet their, friends and relatives, it's a whole nother thing. And so they've been to the factory many times to see their rocket, and it means a lot to my employees to know them and to know that we're flying people, and so we're just that much more careful. And we have pictures of them everywhere to sort of remind us, that's Sunny, that's
Sunny's
that's
amazing,
Nikki.
isn't she?
Yeah.
She really is.
Yeah. Here is sort of the completed product. Stainless steel. You can see it's still, just look at that.
I didn't ask, I'm allowed to touch, right?
You can touch it, yeah.
Okay. Okay, is that machined after it's welded?
Before.
Before?
Yeah, before.
Okay. So you make a groove, maybe?
Yeah,
Gotcha.
and we actually plane the whole surface. So as thin as that was, what you saw over there, we actually plane it and thin it out just a little bit more. We want it a little thinner than you can buy it.
Really?
The cool thing about Centaur is, a booster is typically 80% mass fraction. And most upper stages get 85-ish. Centaur's around 90. So literally the highest performance upper stage ever. Okay, so we saw the dome. That's the cylindrical tank that dome will be fitted to. One on the top, one on the bottom, and the one on the bottom is where the engine will be.
Is this the same thickness metal that
It
we're talking
is,
about?
yeah. So that giant thing you're looking at, 40 feet long, half the thickness of a dime. You see all the rings? That's all tooling so that we can support that shape so it doesn't just collapse on its own. And when we actually put the domes on it, we'll have to grab it at either end and stretch it or pressurize it, depending on where it is in the factory.
Oh, okay. So it's the opposite of a bulk buckling problem. You have hoop stress and you have ring stress. Ring stress is the issue here.
Exactly.
Okay.
Exactly.
Wait, am I saying that right? Okay. So you have axial stress and you have ring stress, and ring stress is the problem.
So you could think of it as a longitudinal buckling problem if you want, because the weight of the structure itself would overcome the stiffness, and you'd start with a hoop and it would just kind of buckle like this on the top and fold in.
Gotcha. Awesome. But we have the same friction stir welding idea
No.
there?
So this material is so thin that you cannot friction stir weld it. So this is all done with resistance arc welding instead. And on Centaur 3, which is what we fly on Atlas today, this is a labor intensive operation. 180,000 welds. They're all set up by hand, so it takes many, many hours and quite a bit of time to build this sort of Ferrari of an upper stage.
Yeah.
Vulcan will be robotic and automated.
Really? That's amazing. Dome on the front, dome on the back, tank. The engine, well, there's not a dome on the back. That's where the engine goes.
So there'll actually be a dome so that you have a sump to collect propellant in to draw it into the engine so you don't waste as much propellant. And what you can't see on the inside is a bulkhead to separate the liquid oxygen and the liquid hydrogen from one another.
Got it. So where are the engines at? Are they here?
Let's see. Have we got an RL-10 open out of a crate that we could show him?
We're gonna go upstairs.
Okay. Oh, yeah. So we're gonna. So there's a final assembly that gets done in a clean room.
Okay.
And that's the best place. So we'll look down, you'll see a whole bunch of them, there'll be engines, that'll be better. Okay, so this is the final assembly area for Centaur. This is a clean room, that's why we're up here. The people down there who are on break right now would be in bunny suits. So you're looking at the business end. Those red covers are on the bottom of the nozzle of the RL-10 rocket engine. And you can see that you have a standard configured one with a single engine
Right there.
right there, but to its left you see a dual.
Okay, that's strange.
That Centaur will carry astronauts to space.
That one will.
That one will.
That's amazing.
Yeah.
That's a pretty big deal. So how do you, I mean, that changes everything about how you operate the thing. Have you ever flown a dual engine Centaur?
We have, but it's been decades.
Really?
And so this is reintroducing a kind of a historic, but one configuration we haven't done recently.
So this right here, I'm seeing, that's Mars 2020 right there.
Yeah.
So that's the Centaur that's going to take Mars 2020 to
Yes,
Mars?
it is. Yes, it is.
So you do the bulk of the heavy lift, or I guess the far push, you could say, with Centaur.
We do. Yeah. So the booster's job is to get you into space, typically, depending on the payload, but typically you're not quite orbital at the end of first stage burn, and then Centaur will take you orbital, bring you to your parking orbit, and then once you're lined up correctly with the right sort of argument of perigee, then it will send you off on the final burns to get you lined up for wherever you're going. In this case, it's interplanetary mission, so we're going out to Mars.
So the brains that drives the Centaur, where is that at? Are you integrating GNC at this point?
We are. So on the back end of that is a flight controls computer and inertial measurement sensor and other sensors, rate sensors that are the guidance system. They're always attached to the upper stage, obviously, because if you attached them to the booster and separated, you would have lost your brains. So they're always up here.
Okay, final assembly. And
yes.
I'm not, yeah, so this is the big show, right?
This is a big show. We call this the Great Hall of Rockets because, as you can see, there's rockets way down there and they just keep going all the way to that big roll-up door. And as they go, they're in final assembly, and when they get to that door, they roll outside, down to the rocket ship, and off to the launch pad.
So this gentleman over here is doing final assembly on a rocket.
He is absolutely doing that. Yes, he is.
That's amazing. And so, wow, just having a person for scale is pretty impressive there.
Yep.
That's amazing. So what are we looking at? These are
deltas on this side of the aisle, and atlases on this side. And way down there, we'll walk you back down there, but Vulcan will start at the far end of the Delta line and slowly work its way down, eventually replacing Delta entirely.
So Delta and Atlas are being phased out, correct?
Yes, yes.
So do you know the number of missions you have left for each one?
I do.
Okay, are you allowed to talk about it?
No.
Okay. So the last question I asked Tori was very interesting. And before I show you that, though, I want to say you should be following this guy on Twitter. He has a legitimate technical engineering answer for everything he's asked. He's very engaged in the space community. It is legitimately fun to watch Tori Bruno interact on Twitter. So there's that. Now, if you're into space, you know that I didn't ask two things in this video. I didn't talk about engines very much, and I also didn't ask about Tori Bruno's competitors. I did that. That's over on the second channel. He gave me really good answers. If you want to hear what Tori Bruno thinks about those two things, go to the second channel, link in the video description, also a link to Tori Bruno's Twitter. Okay, let's get back to the last question I asked Tori on this tour. I have noticed that there's not a lot of stuff in this plant that's going to low Earth orbit.
That's correct.
And that's intentional?
Yes, our specialty are the higher energy, more difficult orbits, things like Mars 2020, the interplanetary mission.
Right, and that's
literally right there, yeah. But we don't call it Mars 2020 here.
What do you call it?
We call it Mars 2020-20.
Why would you do that?
Because it's our 20th trip to Mars.
Really?
Mm-hmm.
That's amazing. That's impressive. And so your job is to get it there.
Yes.
And then what happens with the payload at that point is?
So it'll re-enter, it'll come down to the surface of Mars. As you mentioned, it's a rover. We really set it on its way. So Centaur's not going to go all the way with it to Mars. We're going to put that energy in as an escape velocity here at Earth, a greater than 1c3, as we say in the technical world. And then that will carry it all the rest of the way. It will establish its own orbit and land.
That's impressive. That's what I like about Tori. He knows his stuff. So thank you very much for this tour.
Oh, yeah.
This was
You're welcome.
Absolutely incredible.
Yeah.
I've lived near this plant my entire life. Well, I guess it hasn't been here my entire life, but as long as it's been here, I've lived near this plant and always wanted to come inside. So thank you very much for extending your flight and giving us this tour. This was amazing.
I'm glad you came by.
Thank you so much.
You bet.
Super duper thank you for watching this video. It's a long video, but it's so special. I mean, I've loved rockets forever. Always have, always will. And this is like rockets and manufacturing, the Venn diagram right there, that sweet spot. This is what this is for me. It's wonderful. So thank you for watching this video. If you feel like this type of video earned your subscription, one way you can signal that to me is by subscribing. You can click on the subscribe button and there's a little notification bell. If you click that, it'll notify you when I upload, and that'll encourage me to do more stuff like this. Big thanks to ULA and Tori Bruno. You trusted me with your rocket factory, so thank you very much. Also, you can support on Patreon if you're into that sort of thing. I've got something coming up in the near term that the patrons have made happen, and it's fantastic. Audible.com/smarter, or text the word smarter to 500-500. I recommend Seven Eves or Mary Robinette's book, The Calculating Stars. Yeah, that's about it. I'm just really happy and very grateful, and thank you for being here with me. That's it. I'm Destin. You're getting smarter every day. Have a good one. Bye.